Hey, we have here today another integral from the MIT Integration Bee. This was from 2023, regular season 17. We have the integral from 0 to 5 of -1, all to this exponent, which is the floor of x plus the floor of x over the square root of 2 plus the floor of x over the square root of 3. Okay, so we have quite a bit going on here with this exponent. We're using the floor function. And what I thought I would do to start with this one is look at a similar integral that's just a little simpler, which maybe will help us get a better sense of this situation. Okay, so what I wanted to use here was this integral over here, which of course has the simpler exponent. We're just looking at the floor of x, but this is going to be really similar because we have the floor function and we have this -1 here. And what I want to try to do is just graph this -1 to the floor function, because the graph is usually helpful with the floor function to just get a sense of how everything's working. Okay, so to start with, we'll start at our lower bound here, 0, and plugging into x. So like everything from 0 to like 0.999 with the floor function kind of rounds us down. So everything all the way up just to before 1 is going to round us down to 0. So in that region, we're looking at -1 to the 0, but that's just going to be 1. So we're going to have this, so we'll have this line right here at 1. And then next, if you plug in 1 here and any fraction up to like 1.999, all that stuff, the floor function is going to round us down to 1. -1 to the 1 is going to be -1. So our curve's going to continue here at -1 all the way right up to 2. And then similarly from 2 to 3, everything in that region, the floor is going to round us down to 2, -1 squared. And then all this is going to be up here at 1 again. This pattern would continue on forever, but our bounds just go to 5. So let's just graph it all the way to 5. But from this graph, it'd be really easy to calculate the area because we're just going to have these blocks. If we look at it as just trying to get the areas, just roughly, like the area here is going to be 1. This is going to be 1, but it's in the negative, so -1. So this and this is going to give us 0. These two together are going to be 0, and then we would just have the last area. This area is going to be 1. So just looking at the area of this curve, the whole thing together is going to be clearly just 1. Now, a few things I want to notice from this graph, there's only two values, right? Everything's either 1 or -1. That's just because of this -1 raised to integer exponents. This function is going to work the same way as this, where it's just going to be bouncing between 1 and -1. The difference here is, notice here that the width of every integral is the same. This width is 1, this width is 1. We're just using integer values. But here, because we have square root of 2 and square root of 3, the widths are going to be all different values. So it's not going to be as easy to calculate the area, but we still are going to have this same kind of up and down shape. Now, since calculating this area is not going to be quite as easy, what I wanted to do is kind of use these endpoints. And notice that like we've broken this up. Let's just call like our 0 value A, B, our C value will be 2. We'll just kind of label each of these endpoints. But because all our values are either 1 or -1, we can actually calculate this just in terms of the endpoints. We can actually break this up into 5 integrals, but how it's going to work is like if we have one of these integrals, let's say from A to B, and our value of it we know is 1. So when we integrate this, we have x valued from A to B. So our area of this is just going to be B minus A. Well, we can go through each of these and calculate the area just in terms of the endpoints. So like, for example, as we just determined that our first one, this is going to be the same thing as B minus A. And the second one is going to be, of course, C minus B, but we have a minus sign, so I'm going to reverse those and write it as B minus C. And then here for this one, this point's D, so it's going to be, we're going to have D minus C here. And then here, reversing again, we're going to have D minus E. And then here, the area of this one's going to be just F minus E. Now I'm just going to rearrange this so we put these all in order. And so of course I can factor a 2 out of that and just write it with our 2 out front. So what this does for us is it just allows us to calculate the area just from the endpoints, just adding things up and changing the signs as we go. But what you'll notice is this exact same thing is going to work for our problem. Because we have the floor and everything, we're just going to have integer values on a -1. And every time we go up a level on any of these, we're going to be switching from odd to even to odd to even. So the exact same thing that worked here is going to work here. We just have to find out what all these endpoints are. Okay, so now after all that, we can actually look at this problem and we just need to get down to finding the endpoints. That's all it's going to be. So start with the points that we know. We know that we've got a 0 here that we're starting with, and we'll just have a number line. And this is going to go all the way to 5. Looking at this, everything from 0 to 0.99 is going to round down to 0. This is going to be 0. This is going to be 0. This is going to be 0. When we reach 1, this is going to be 0. This is going to be 0, but this is now going to be 1. So we're going to have -1 to the 1, and the sign's going to change. So we'll mark our first endpoint, well, our first endpoint 0, but then we're going to have a point at 1. Then next, when we reach square root of 2, then this one's going to become 1. This is already 1. This is still going to be 0. So then our exponent will become 2. It'll be even. We'll have -1 squared. So we'll have another point at square root of 2. Then it's going to change again at square root of 3. Just noting that square root of 2 is like 1.414. Square root of 3 is 1.732. So then after that, the next thing that's going to happen is we're going to come to 2. So we'll get to 2, and then this exponent's going to become 4. Okay, so we'll have another point at 2. Then at this point, we'll have 2 square root of 2. Then we'll have 3. At 2 times square root of 3, this becomes 2. So 2 times square root of 3 is around 3.4. So we'll write that in right here for 2 square root of 3. Then we'll have our point at 4. Then we're going to have 3 square root of 2 right around here somewhere. So 3 square root of 3 is going to be like 5.2. So that's going to be off the chart here. So our last point here is going to just be 5. So really all we need to do is just take this number line and just add everything up with the pattern we found earlier, and that should be it. So let's just do this in order to finish it off. So we'll subtract our first one, which is 0, which is kind of pointless, but we'll just include it just because. Then everything in the middle is going to be multiplied by 2. So we'll bring the 2 out front. Then we're going to be adding 1, subtracting square root of 2. So we'll add square root of 3, subtract a 2, add 2 square root of 2, subtract a 3, add 2 square root of 3, subtract a 4, add 3 square root of 2, and then we're just going to subtract 1 of the 5. Now we just need to combine like terms. Of course, I'm going to cancel off that 0 because that does nothing for us. So we'll bring our 2 out front. Then 1 minus 2 minus 3 minus 4 is going to be a minus 8 here. 2 square root of 2 plus 3 square root of 2 is 5. Minus 1 is going to be a plus 4 square root of 2. And then our square root of 3 terms, just 2 square root of 3 plus square root of 3 is going to be 3 square root of 3 minus 5. Distributing in first, we'll go to here. I'm going to have 2 times 4 square root of 2 is 8 square root of 2. 2 times 3 square root of 3 is 6 square root of 3. 2 times minus 8 is minus 16. Minus 5 is minus 21. And that's it. So unusual problem, we actually spent a lot more time on the initial simpler example. But then by the time we got to this problem, we just had to add up the number lines. So that's it. Thanks everyone for watching today. Have a great day.